In today's world, it's common for applications to make remote calls to services running in different processes or even on different machines. In a distributed environment, calls to remote resources and services can fail due to a variety of reasons, be it network connections, timeouts, or the resources being temporarily unavailable. What could make matters worse is if you have many callers to an unresponsive supplier, it's possible your system could run out of critical resources, leading to a cascading failure across multiple systems, also known as a snowball effect. These types of faults commonly resolve themselves after a short period of time, and any robust cloud application should be prepared to handle them by using a strategy such as the retry pattern or many other strategies. However, there also could be situations where faults are due to unanticipated events, and situations like that might take much longer to fix. In these tough situations, it might be meaningless for an application to continually retry an operation that is unlikely to succeed. So instead, the application should quickly accept that the operation has failed and handle this failure accordingly. The circuit breaker pattern can prevent an application from repeatedly trying to execute an operation that's likely to fail. In this lesson, we'll implement the circuit breaker pattern using an interceptor bound to an endpoint that tries to invoke a remote service. So let's start off by generating the circuit breaker interceptor using the Nest.js CLI. You can notice that we're passing the no flat flag here so that the CLI creates a new directory named circuit breaker inside of the interceptors folder. We'll use this directory to group circuit breaker feature related files. Next to this interceptors file, let's create a new circuit breaker TS file. Inside this file, let's start off by adding some constants that will determine our circuit breaker's behavior, where success threshold represents the number of successful operations, which once we've risen above, we should close the circuit. Failure threshold, which represents the number of failures, which once we've risen above, opens the circuit to start repeating the last error instead of executing the route handler. And open to half open wait time, which is the number of milliseconds after which our circuit breaker changes to the half open state from open. We'll enter in 1 minute in milliseconds here. Next, below these constants, let's declare an enum that represents our circuit breaker state. As we can see, we have 3 different states here. Closed, which is the default state, meaning that the circuit breaker is closed, aka not enabled. Open, which represents when the number of failures reaches the specified threshold, enabling our circuit breaker. And lastly, half open, indicating when the circuit breaker is in the middle of transitioning from an open to a closed state. Finally, let's declare the actual circuit breaker class with a few useful properties. State, which represents the current state of the circuit breaker. Failure count, which is a count of the number of failures. Success count, similarly, the number of successful operations. Last error, which stores the last thrown error. And next attempt, which represents when our circuit breaker should transition from closed to half open state. This is done by combining the current time via date.now and adding the wait time that we've established. Next up, let's declare 3 methods inside that will handle some of our logic. Exec, which wraps the execution logic, taking the call handler as an input argument and applying the tap operator, which, depending on whether an error was thrown, will call either the handle success or handle error methods. And handle success and handle error. So let's start by implementing the handle error method. Inside this method, let's make sure we first increment the number of failures. Next up, let's add the following condition. What we are trying to deduce here is that if the number of failures reaches our threshold, or if the current state of the circuit breaker is half open, then we need to update the state to open, save the last error that occurred, and we need to update the next attempt property, which, as we mentioned, is the current time plus our wait time. Great. Now onto the handle success method. First, let's reset the number of failures back to 0. Next, let's check if the current state is half open, and if so, we need to increment the success count property. And lastly, we need to test whether we reached the success threshold, and if so, we need to change the state to closed and reset the success counter. Perfect! Last but not least, let's add the following condition to the exec method. If the state is open, meaning that the circuit breaker is turned on, then we check to see if we have reached the next attempt date, and if not, let's rethrow the last error that occurred. Otherwise, everything's all set and we can update the state to half open. And that's it. As we can see, we had quite a few conditions and situations we had to account for. But after all, the circuit breaker is doing quite a few things for us and helping us dramatically improve our retry strategy, so it's definitely worth it. Let's make sure to save our changes, and let's head over to our circuit breaker interceptor class. Inside this class, let's create a circuit breaker by handler collection using a weak map collection. Generally, we'll have an individual circuit breaker instance per route handler. This is why we ideally want to have a collection like this, where we can store which circuit breaker belongs to which route handler. Inside the intercept method, let's retrieve the currently processed route handler using the execution context by calling the getHandler method. Next, depending on whether the circuit breaker exists already or not, we either retrieve it from our internal collection or instantiate it and update the circuit breaker by handler map. And finally, let's replace the last line of this method with the following: delegating the execution of the circuit breaker itself. And that's it. Now, for demonstration purposes, let's navigate to our Coffee's controller and annotate it with the Use Interceptors decorator, passing in our circuit breaker interceptor inside. Next, let's simulate that our findAll always returns an error, replacing the current method implementation with the following. Perfect. Let's save our changes, make sure our app is running, and in a separate terminal window, let's call our endpoint 50 times using curl. As we can see, for all these calls, we received the 408 request timeout error. However, if we switch back to our application's terminal window, we can see that our endpoint was only executed 3 times, as that was the threshold we declared in our circuit breaker file. It worked. So as we can see, the circuit breaker we built did its job and kept returning the last error message, which was 408 request timeout, instead of constantly trying to hit the service that's unavailable at the moment. In our case, since we have forced this issue ourselves for demonstration purposes, we are not seeing the service recover and the call becoming successful, which eventually we would hope it would. But you can see with what we've built here in a real-world scenario, if this endpoint was reaching out to an external service, once that service fully recovered, everything would return back to normal and eventually we'd get a successful response back from that service. Hopefully everything we've covered here helps demystify and show the value of this circuit breaker pattern to you, as it's an excellent strategy for improving systems' ability to handle faults, errors, and other downtime problems.